My name is Alex Razoumov. I'm a visualization coordinator for WestGrid, one of the consortia in Compute Canada. So I'm based at Simon Fraser University in Vancouver, and you can get in touch with me. So the email address alexrazumov@westgrid.ca. The copy of these slides you can download as a PDF file. So the address is on the screen. It's bit.ly/batch slides. So it's a link to a PDF file. And I try to include all codes into the slides. So the longer ones that couldn't fit into the slides are available as a separate zip file download. So if you go to bit.ly/batch code, that will download a very small, it's only something like 10 kilobytes or something like that. Very small file with several codes inside. So the topic of today's presentation is Introduction to Batch Visualization. And really, the topic should be, the proper topic should be batch processing and visualization of data with scripts on remote clusters, preferentially without opening any windows at all, so doing it completely from the command line in the background. So the talk is going to be given from a WestGrid perspective. I'm going to show several examples on the cluster called Parallel. So it's one of the newest clusters in WestGrid, and it has a number of GPU nodes. The same ideas will actually apply to batch visualization on your desktop. And so the couple of examples I'm going to show you, I'm actually going to develop the scripts on my desktop. So you will see how I develop the scripts, and then I will show you how to run them on the remote system on Parallel. So in principle, all of the scripts can be ported to any cluster in Compute Canada. So whether this cluster has a GPU or if you're doing rendering entirely in software based on CPUs. So setup might be different depending on the cluster. If you have any questions, if you need help porting these examples, or perhaps writing your own codes on any cluster in Compute Canada, you can always send an email to me, or you can ask your local consortium for help. So whether it's WestGrid, SciNet, SharkNet, AceNet, Calcul Quebec, or HPCVL. So, for example, in WestGrid, we have a local consortium support mailing list, a ticketing system. So just any email that goes to support@westgrid.ca is going to generate a ticket and a quick response. In SharkNet, for example, it's help@sharknet.ca and so on. Also, I want to mention that we have a countrywide visualization mailing list, vis-support@computecanada.ca. So these emails will go to everyone, well, all techs who are interested in visualization everywhere in Compute Canada. So currently we have about 10 or perhaps 12 people on this mailing list. And so somebody will answer your question fairly quickly. I assume that you have data sitting somewhere on a cluster. So perhaps it's an output from a large simulation running on the cluster. Perhaps it's even an experimental data set that you copy to a cluster and you just want to visualize it. So why would you be interested in doing remote visualization? Well, there are several reasons for this. So the first one is data set could be just too big to download, especially for large projects on a regular basis. If you're generating, let's say, terabytes of data, it's going to be a waste of bandwidth and time trying to download all this data to your desktop, because you can do visualization and analysis on Compute Canada systems without moving any data. So another reason is if your data set is too large to fit into desktop's memory. So for example, let's say you're doing, a fluid dynamics simulation on a 2000 cube grid and you have several variables. So these won't certainly fit into a visualization package on your laptop. So you will have to be smart how either you download just part of the data set, or you can visualize the entire data set, but you'll have to do it remotely on a cluster. So perhaps rendering on the desktop is just too slow. So because you have limited CPU and GPU power, and in this case, you can either run a longer visualization rendering job on a cluster. Say, let's say you start a job and come back after a few hours, perhaps a few days, and then you have a nice visualization. Or perhaps you can even submit several visualization jobs running at the same time, and they will be rendering, for example, multiple frames of a movie at the same time. So perhaps you're also doing, you might be doing in-situ visualization. So by in-situ visualization, we mean modifying your simulation code so that it outputs graphics directly, or perhaps it outputs, or perhaps instrumenting in such a way that you can connect to a visualization client on your desktop while the simulation is running. So such capability exists in popular packages such as ParaView and Visit, and I'll mention briefly if I have time in the rest of the talk. So finally, if you're interested in visualization using one of the commercial packages, we have a number of packages installed in Compute Canada. For example, on WestGrid, there is an expensive visualization package called Aviso. It's expensive, so we have, unfortunately, just a single floating license, but you can certainly use it. But you have to use it via some sort of remote desktop solution. So, and I'll show you how to do this. And then if you're doing remote visualization, so presumably via a batch job on a cluster, you'll get all the usual benefits of scripting. So things like automating a mundane or repetitive tasks. For example, if you have multiple time slices, time outputs from, let's say, time-dependent simulation, and you want to process multiple frames for a movie. So you can develop a visualization workflow for a single frame, and then you will just wrap that into a loop in a script, and I'll show you an example how to do that. Also, perhaps you just want to do visualization without opening any windows at all, and you can certainly do that with remote visualization. There are many different visualization tools, and many of them let you script the entire workflow. So they have a programmable interface, whether it's a compiled language such as C++, or an interpreted language such as Python. And so as long as there's some sort of programmable interface, all of these visualizations can be scripted on a cluster. So several domain-specific packages support scripting. For example, DMD, a very popular open source package for visualization in molecular dynamics, provides interfaces in Python and TCL. And so you can actually write scripts that will run as scheduled background jobs on a cluster. Because I'm not I'm giving this presentation to a wide audience. I'm not talking to an audience, let's say in chemistry, biology. I can't really talk much about these domain-specific tools. The rest of the talk is going to be about general purpose visualization. And when you talk about general purpose visualization, you certainly have to mention VTK, Visualization Toolkit Library, which is extremely popular, and it actually serves as a base for several other really popular visualization packages such as Visit, ParaView, MyVI. And so not a lot of people know this, but you can actually script the entire visualization workflow using just one of the languages that you see on the screen, so C++, TCL, Java, Python, and you will call VTK library functions directly from this language, and you can actually do everything, the entire visualization workflow, entirely using just the VTK library and nothing else. MyVi or MyVI, not sure how to pronounce it exactly, is a popular serial, so not parallel, three-dimensional scientific visualization package. So it has an embedded Python shell, and it's been quite popular, back in the 90s, early 2000, and it's really powerful. So the only problem, as I said, it's not parallel, so it doesn't really scale to very large visualizations. And of course, when you talk about general purpose tools, you have to mention Visit and ParaView. So these have become standard visualization tools for large three-dimensional scientific data visualization and analysis on a wide variety of systems, from laptops to really large distributed memory clusters. And there's a good reason why they're so popular. So both of them are both of them are open source. They are under active development. They can visualize a huge variety of data. So for example, scalar fields, vector fields, tensors, tensors of tensors, something else. And these fields can be defined on a large variety of different discretizations. So for example, you can have data defined on a regular three-dimensional Cartesian grid, or some sort of unstructured grid, for example, an unstructured triangular mesh, or perhaps data is defined on particles or some irregular topology, like some weirdly shaped cells that you can define yourself. So these data sets support visualizations up to very large data sets, going to many, many terabytes. And of course, to visualize terabyte-sized data sets, you have to, these tools have to scale to a large number of processes. So both Visit and ParaView have been parallelized with a message passing interface, which is now an industry standard for parallel computing on distributed memory clusters. And both of them have been shown so Visit and ParaView have been shown to scale to thousands of processes quite efficiently. So both of them have a very nice interactive GUI. They support scripting as well. They can work in a client-server mode, so that means that you can start a client on your laptop, for example, and the server will do all the heavy lifting on the remote cluster. They support a huge variety of input file formats, so things like netcdf, HDF5, tools from various domain-specific, file formats from various domain-specific packages. So they have support for parallel I/O. That means you can read, for example, a large file from many processes at the same time. And they have a large number of different visualization features. So you can do things like visualize surfaces, visualize volumes, visualize vector fields. And I mean, there are really probably more than 100 different features in each of these packages. And both of them are based on VDK support. So the only difference between, one of the differences between Visit and ParaView is that ParaView was written by the same folks who developed VDK. So there is really a tight integration between the two packages. This seminar is in this seminar, I'm going to use ParaView to show the examples, simply because for the past few years, we've been using ParaView to teach visualization in our member universities of Compute Canada. And so this talk is just going to be an extension of our usual training. So just a couple more words about ParaView. So it was started 15 years ago as a collaboration between Los Alamos National Lab and a private company called Kitware. And it's really meant for visualizing extremely large data sets on distributed memory systems, so on high-performance computing systems. But it works equally well on a desktop. It comes as you can download a source code, compile it yourself if you wish on your laptop, for example. It's fairly easy to do. And it's also available as a binary distribution on any platform, Linux, Mac, Windows. So it has a very nice GUI. I'll show you in a few slides. Supports scripting. And as I said, it's based on MPI, so it can actually scale to a very large number of processes. In this webinar, I assume that because we don't really have a lot of time, I assume you're already familiar with ParaView basics. You know the main elements of GUI, how to load a data set, how to switch between different views, for example, a volume rendering view, a points view, a surface view, wireframe view, and so on. How to color the data set by a variable, how to use filters to build a visualization pipeline, and so on. So if all of these things are new to you, then here I have in this slide the links to our standard teaching materials. So the first one, PV slides, is a link to my usual full-day visualization workshop. Then PV archive is a link to the associated sample data sets and codes. And of course, you can also find a lot of information online. So for example, the last link is shows you, is a link to ParaView's standard documentation page where there are lots of user guides, tutorials, and so on. So I also want to say that a lot of people who look at ParaView, they don't realize that they don't really, in many cases, ParaView is really an overkill. So if you don't need a three-dimensional visualization, if you're just plotting one-dimensional functions, or perhaps a function of an image, a function of two variables, then you can easily do that. You can do that in ParaView as well, but ParaView is really an overkill for that. So you can do that in many libraries for R package and for Python. So for example, here I have a simple Python script that shows how you can do a batch visualization of a one-dimensional function. So just function f, y is equal to f of x on a cluster. So here the trick is that you have to use a backend, so-called backend in Python, Python's matplotlib library, which doesn't require a windowing system. So usually when you try to do any visualization, well, any plotting from Python's matplotlib, by default it will open a window. But if you switch to a PNG backend, which is called ARC, so the example is on the screen, or a PostScript backend, or a PDF backend, the image will be written directly to the file without opening any windows. And so if you connect to a cluster and just copy and paste, well, start Python there and copy and paste the script, you will see what I mean. And of course, you can build fairly complex visualization workflows for one-dimensional and two-dimensional problems. So ParaView is really about three-dimensional scientific visualization. So to understand how to run it remotely, I have to mention that ParaView has three components. There is a data server that reads data from disk, perhaps in parallel, perhaps in serial, that filters the data, does some manipulation, well, applies some calculators to it, for example. And there's also a render server that is a unit responsible for rendering. So basically, it converts your various surfaces and polygons into the pixels on the screen. And then there's a client. So usually a client is an interactive GUI package that you're sitting in front of, and you're interacting with it using your keyboard and mouse. And in principle, all the three components can run in a single application. So if you start ParaView, for example, on your laptop, then the data server, the render server, and the client will be part of the same application. But in principle, you can also run the data server and the render server on a cluster remotely, and then connect to it from the client. So if you have data on one of the clusters, so apart from downloading the data set to your machine, which is not really a good solution for large data sets, you can certainly just log into to the cluster. So you'll find yourself on the login node. And if you enable if you enable X11 forwarding, so you log in with the option so SSH minus X or SSH minus Y, that will let you open Windows remotely from the cluster using the X11 server on your laptop as a windowing system. And so any window that you will open will be actually displayed on your machine. But so this is what most people actually who just start with visualization on clusters do. It's very easy to do, but it's not the most efficient way to use visualization. So I'll talk why in a few slides. So we really recommend one of the last three methods that I have on the slide. So the first one is remote visualization via VNC, or perhaps some other remote desktop option. So VNC is by far the most popular. It's open source, and we have it enabled on the vast majority of classes in Compute Canada. So I'll show you how to do that. I'll show you an example very soon. So another way to run ParaView remotely, to do visualization remotely, is to run the server on the cluster and the client locally on your laptop. And then you organize communication between the two. So basically you organize SSH port forwarding that will connect the the ParaView port on your laptop to the ParaView port on the cluster, and then all data will be sitting on the cluster. All heavy lifting will be done by the ParaView server on the cluster, and then visualization will be, you will see visualization interact with it on in the client on your laptop. Let's go to the first example. So what I will do, I will do some visualization interactively on my laptop. I will build a script corresponding to that visualization, and then I will show you how to run, actually several different ways to run this script on the parallel cluster in WestGrid. So the visualization is a mathematical function of three variables, x, y, and z, defined in a unit cube. And the function is given by, this mathematical expression. So I have a code inside the batch.zip file. So again, the link for those of you who joined later is in the first slide. And also I see Aaron pasted the links into the chat window. So the link is the last one, bit.ly/pv archive. Will download a batch.zip file that you can download, unzip, and you will see several examples there. So to compile the example, you need a netcdf library. So that library is installed on pretty much any cluster in Compute Canada, and you can also install it locally on your machine. So I'll just run an example on my laptop, and then running the code. So I'll compile the code first, then I will run it. That will generate the file called signenvelope.nc. So that's a netcdf file that samples that function at 100 cube resolution, so regular Cartesian grid. Then I will import that netcdf file into ParaView, and then I will play with several different views, and then I will use the trace tool to build the visualization. Let's see. for some reason, decided to share my, okay, let me try to go back. Okay, so hopefully now you see this slide that says demo time. So I will start ParaView on my laptop. And before I actually load data, I need to generate the data set first. So here I already have a makefile that will compile the code. So now I have the code called example.1. I will run it. And that generated the netcdf file, which is almost 4 megabytes in size. So that's single variable 100 cube resolution. And then I will load that file into ParaView. So let me navigate to the file, Sana envelope in the C. So it's netcdf file generic. Press OK, click Apply, and then I'll switch. Let's switch first to surface view, and then color the data set by variable. So here's the outer surface of my data set, of my unit cube. And let me first do isosurfaces, just to show you how to do it. So I click on the contour filter, I click on Apply, and actually let me specify an isosurface, let's say at the value of the variable 1.4, the value of the function 1.4, hit Apply, and then I also need to enable to pass scalars through the filter to color by the function. So here's a nice visualization. So we're looking at an isosurface of the function. So again, it's a function defined in a unit cube. If you look at the function itself, you will see that it's actually symmetric in x and y. So there are two terms in this expression. The first term contains x and y. The second one contains y and z. So y is a non-symmetric variable, but if you switch x and z, the function will not change. And you can see that indeed along the x and z directions, the function is symmetric, and it's somewhat special along the y direction. So for developing the script, I will actually switch to volume rendering. So to do that, I need to delete the contour filter, and then I will go to volume. So here's volumetric ray tracing. So what I will do next, I will go to Edit Color Map and switch to a nice color map, and then I will play. So I introduce a new point in the color map, and I'll play with the brightness of the color map in such a way that I display only the high values of the function. So let's see. Yes, here it is. So here's what I want to see. And so now I want to develop a Python script that captures what I just did. So to do that, I will erase everything. I'll repeat the entire procedure without the isosurface filter, just the last visualization. And before that, I have to enable the trace tool. So I go to Tools, Start Trace, then All Properties, including supplemental properties. So I started the trace tool, and then I will just load the file again. So it's sign envelope, netcdf files generic, press Apply, switch to volume view. Then I will load a different color map, and then I will introduce a point here and modify the brightness in such a way that I show only the high values of the function, and then I'll spin the object around a little bit, and then I stop the trace tool. So when I stop the trace tool, it gives me the Python code that corresponds to exactly what I just did. So the code is fairly long, and not all of these things are important, well, for our purposes. So I actually have an optimized version of this code in the file spin.py, which you can find inside the batch.zip file. And so here's what it looks like. Let me just bring up in my text editor. So we load so this is the Python script which corresponds to the visualization that I just performed. So we load the file, the netcdf file. Then we switch to a volumetric view. We color the data set by the function itself. And then, so this paragraph corresponds to loading a different color map, an ISO color map. So in ParaView's Python, there is no single command to do that. So you have basically to specify to describe the color map itself. And then we introduced a new point highlighting only the high values of the function. So this is this command. And then finally, we spin the object around a little bit. So that corresponds basically to setting the location, location direction of the camera view. And then we save the screenshot to a file called test.png. So when I run this script, it will generate the file test.png in my working directory. And so how you run this script is, well, there are actually quite a few different ways in ParaView. So the first one, each ParaView, pre-compiled version of ParaView comes with a tool called PVPython, which you can find either, so for example, if you have ParaView on Linux, you can find it in user bin directory or in user local bin directory, depending on where you installed it. So on a Mac, it's found under Applications, ParaView app. In Windows, it will be found somewhere under the programs, so you can actually run it from the DOS shell. And then, so if you start PVPython, it will just give you an interactive Python shell where you can copy and paste the commands. So, of course, if you have the script already saved in the file, the easier way to run it is instead of using PVPython, you can use the pvbash command followed by the script name. So let me just show you how to do this. So I do something like, here I say application, so that's on my Mac. I need to specify the path to pvbash. So here it is, pvbash, and then spin.py. So that will run the script. So it's currently running, okay? And then it generated a file called test.png, and here's the visualization that my optimized file spin.py produces, okay? So what I want to do next, I want to make a movie out of this visualization. And to do this, I will use a function in ParaView's Python called getActiveCamera. So anywhere inside the Python shell, inside the ParaView's Python shell, you can actually use the help command to get more help on any function or any object that you have loaded. So for example, if you type help and in brackets get active camera, it will tell that this function returns the active camera for the active view. So basically, it returns an object that you can use to specify the camera position, for example, or print the current camera position. So if you type dir get active camera with the round brackets, it will give a number of attributes or fields and method functions of this Python object of class VDK camera. So the important ones that I want to draw your attention is azimuth and elevation. So these are functions that will let you specify the position of the camera, so basically the orientation of the data set. So you can get more information about these functions if you type something like this: help, get active camera, round brackets, dot azimuth. So that function rotates the camera about the due up vector, so basically around the vertical vector centered at the focal point, so that is the data set. And so what I'm going to do, I will just take the spin.py script and modify. I will replace, this is funny, it doesn't show now. Huh. Don't know why it doesn't show. So I will replace the last line, which saves screenshot, with the following paragraph in the middle of the slide. So I will call getActiveCamera, and then I will call the azimuth function. So say camera.azimuth of first frame, where first frame is just an integer variable equal to 90. So that will rotate my data set by 90 degrees. And then I organize a loop where the index variable I goes from 0 to 90. So 91 loop iterations. And then inside each loop iteration, I rotate the view, the central object by 1 degree in azimuth. And then I save the screenshot to a file called frame, and then there's some extension based on, containing the index variable. So basically, it will save screenshots going from frame000.png to frame0090.png. So if I run this script, it will generate 91 files that I can merge into a movie. My preferred tool for merging frames into a movie is FFmpeg. It works wonderfully on Linux and a Mac. On Windows, perhaps you can also use it if you install Cygwin, for example. And it will, in this case, so as you can see, I used 91 frames to generate a fairly small movie, it's only 400 kilobytes. And let me just show it. So it will not show very nicely through the this presentation tool, but I'll show it anyway. So hopefully I'll be able to play it back. So there are 91 frames. Not sure how well it plays remotely, but on my local screen I have a very nice movie which is playing for 9 seconds. So the point is that we developed a very simple script from scratch. We ran it locally, and it generated a movie. So now we want to use the same script on a cluster. How do we do this? Let me switch back to the slides. So the easiest way to do this, a couple of words about the parallel cluster in WestGrid. So this cluster is meant for, so it has several hundred regular compute nodes and also 60 specialized GPU nodes for general purpose GPU computing. So each one of these 60 GPU nodes has 24 gigabytes memory, 3 relatively recent NVIDIA Tesla GPU cards, and 4 of these 60 nodes can be used for visualization. Well, they're open to the interactive queue. So what we mean by interactive queue is a queue that accepts jobs not longer than 3 hours. So if you try, you can certainly submit a visualization job to any of the other 57 GPU nodes. The only problem is that those nodes are quite busy for, well, with people who submit jobs just running general purpose calculations on GPUs. So in general, wait times are going to be shorter on these specialized 4 visualization nodes. So before I show you an example of how to run the script on one of these GPU nodes, first I want to mention that you can certainly run this script on the login node. So just log into a cluster. You will find yourself in one of the login nodes. And you can just issue the PV batch command, so call the latest version of ParaView 4.3.1, which is sitting in the global software ParaView directory. And so just pass the spin.py script name to it. And so that will run without problem, but it's actually not a good idea for a number of reasons. So the first reason, and it applies to pretty much any cluster in Compute Canada, is that login nodes are not meant for anything CPU intensive. So they're meant for people for compiling jobs, for looking at the file contents, just moving files around, submitting jobs, but certainly not for anything CPU intensive. So for this reason, usually login nodes have fairly strict restrictions on the runtime of the job can submit and the memory that these jobs can use. So we really encourage people to use actual compute nodes to do anything CPU intensive, including in large visualizations. So another reason why it's not a good idea to run this script on a login node is that the default version of ParaView on Linux requires an X Windows server, an X11 server. And when you connect to a login node by SSH-X with X11 forwarding, when you open a window from the command line on the login node, it will open a window on the inside the X11 server on your laptop. So basically on your laptop's screen. And this introduces unnecessary traffic, and it'll be very slow first, and then it introduces unnecessary traffic, which, I mean, you don't really need this if you do batch mode visualization, right? So you don't really need to see visualization of each frame if you want to run this visualization job in the background. So you can certainly compile ParaView with off-screen rendering support. So there's a library called, open source library, which is called OS Mesa. So it allows you to open X11, well, not to open just to pipe the content of X11 windows directly into image files. But it requires recompiling ParaView, and it's actually more trouble than it's worth, considering other limitations on the login node. So we really recommend that you run such visualization jobs on GPU nodes. So to do this, I'm going to show you 3 different methods. So the first method is to do it interactively on a GPU node. So in parallel cluster, again, this applies only to the parallel clusters. So in WestGrid, the way you would do that on other clusters in Compute Canada will depend on a cluster. So if you're not sure, just let us know. So in this case, what I do, I submit an interactive job to one of the visualization nodes. So -Q interactive makes sure that it goes to one of the 4 visualization nodes. -I, capital I, makes sure that once the job starts, I get an interactive prompt in the same terminal window. And then I specify how many resources, how many processes, how many nodes. So single node, single processor per node, and a single GPU. And I want, so the maximum runtime is going to be 30 minutes. I'm going to use this single GPU and a single processor for not more than 30 minutes. So I hit enter. And then once the job starts, and usually it takes a few seconds, around 10 seconds, 20 seconds on average, unless all of these nodes are busy, which is usually not the case on the 4 visualization nodes that I mentioned. So next, what you have to do is there is inside the job, so inside the shell, you will see a number of PBS variables which are associated with the job you just started. One of the variables is called PBS underscore GPU file. It just points to a file on the Linux file system which contains the name of the GPU that has been allocated to your job. And so you will use the name of that GPU as, well, you basically paste it into the display environment variable, and that makes sure that any window that you open from now on after setting the display variable is going to be sent to a remote, to a virtual display associated with that GPU. So when you open any window, you will not see it on your screen. It will just be rendered virtually. And so when you run this script, so the script is run by the pv bash command followed by the script name. The script will run entirely remotely on the compute node. Rendering will be done inside a virtual window on the GPU, and then it will be written to the image will be written to a file on the cluster. So if you need to debug these scripts, it's well, I want to mention that it's by far it's much easier to debug scripts locally on your laptop. Just the way I showed you in the first example, just starting a local version of ParaView, and then using the trace tool to build a script and then debugging it. So most scripts that you develop on your laptop will actually work with few modifications on the cluster. So in cases when you need to do debugging on the cluster, so the best way to do this, in my opinion, is to start a virtual VNC server on the cluster, and then start a VNC client on your laptop and connect to the VNC server. So that will give you a virtual desktop, which is running as part of the job, in this case on the parallel cluster. And then you will start a ParaView client while running entirely remotely on the cluster, and then you'll be able to use it to debug your script. Yes, so the details for what I just, I will not go through this slide in detail because we don't have a lot of time, and I want to show you another example. But the details are in this slide, and you can certainly, so we have a lot more detail at the page, which is, so you can find the URL at the top of this slide. So the second method for running the script is you can simply submit it as a batch job, right? So you can write a usual PBS job script and then submit it. So in this case, I'll call it visualization.sh, and it's just submit as any other regular job on a cluster. So the only difference from regular jobs is that you will specify which set of nodes, in this case, -Q interactive, will send it to one of the 4 interactive visualization nodes on the parallel cluster. And then, so the rest of the script is fairly transparent. So again, we're asking for 1 GPU, 1 processor, maximum of 2 GB of memory, and the maximum runtime 30 minutes. And so you can simply copy and paste that script into your terminal window on the parallel cluster, and it will work without any problem. So the third method is you can also run the script interactively inside a VNC remote graphical desktop. So in that case, so we advise you to use the VGL run command. So this command will make sure that, so if you don't have a VGL run command, then if you start ParaView inside a VNC session on the cluster, what it will attempt to do, it will try to use the, for rendering, it will try to use the GPU on your laptop. And most likely it will just give you an error because it expects a different version of the graphics driver. Sometimes it will work, sometimes, in most cases, it will give an error. So to make sure that all OpenGL commands, so basically all graphical rendering commands from ParaView, go to the GPU on the cluster, you have to issue the VGL run command. So it's part of the virtual GL package, and basically will just ensure that it will intercept all OpenGL calls and redirect them to the GPU on the cluster. So if you're running visualization on a machine that doesn't have any GPUs, then things become a little bit more complex because you have to recompile ParaView to enable off-screen rendering with the OS Mesa library that I mentioned before. So it's fairly easy to recompile ParaView. And so we haven't done it on each cluster in Compute Canada simply because, well, we just do it based on demand. So if you need to do visualization somewhere on a cluster that doesn't have GPUs, just let us know. We can certainly help you. And so when we recompile ParaView with off-screen rendering, we'll also make sure that we enable a parallel support, MPI support, so that is very easy to do. And ParaView, in this case, will be compiled without the GUI client. We'll just compile the PV batch command, the PV Python command, and the PV server command that will run to, they can use to start the ParaView server. And in this case, the way you will submit, well, you will run the visualization command inside the PBS script is given in this slide. So if you're doing it, if you're doing serial visualization, you will do something like PV batch, use off-screen rendering followed by the script name. And if you want to do visualization in parallel, which is entirely doable, you'll just need to use, say, MPI exec inside PBS file followed by, well, the same commands. So ParaView can run very efficiently with MPI, so in parallel. But the thing is, you have to keep in mind is if you're running it purely in software without any GPU rendering, it's going to be slower, especially for things like volume rendering and, well, complex data sets. So you will have to make sure that it runs fast. You will actually have to throw quite a large number of processes at a job, for example, 10 or 50 processes or something like this for it to be comparable in speed to visualization to rendering on a GPU node. So if possible, if you have access, well, if there are GPU nodes on the cluster where you have your data set, then I encourage you to use GPU nodes as opposed to doing software rendering with CPUs only. Unfortunately, we're running, well, we still have about 10-15 minutes late. I want to show you one more example. And this is important for, so this is important for, it's, the point here, excuse me, the point here is when you load multiple files into ParaView, so let's say you have a time-dependent simulation that produces a number of time slices, time outputs, and then you use ParaView to generate visualization for one of these time slices, and then you wrap that inside the ParaView's Python script into a loop. So you will find that when you do this, you will load at least one object, so your data set, into the ParaView's visualization pipeline. And if you have a very large data set, let's say 1,000, 2,000 frames, then you will end up with a large number of objects in the visualization pipeline in ParaView. And this will actually crash your ParaView. So it will become, first will become very, very slow, unresponsive, and then it will just crash. So it's very important to do proper garbage collection. So I want to show you this in the example. So the data for this example comes from, so it's openly, it's data that is openly available from the U.S. National Oceanic and Atmospheric Administration, so Physical Sciences Division of the Earth System Research Laboratory. And this data shows the distribution of ice sea levels anywhere, well, everywhere on Earth, starting from January 1850 and ending in December 2013 at a 1 degree resolution, both in latitude and longitude. The data set comes as a single file combining all 164 years of data. So 164 years times 12 months per year times 360 degrees times 180 degrees. One single precision variable leads to an almost half a gigabyte file that can be downloaded from the link I have in this slide. So for the purpose of this example, I actually converted the data set into 1968 separate VTK files. So I'll show you, I'll try to load one of these PDK files into ParaView, and then I will organize a loop around that file so that it generates 1968 separate images. Let me just go back to ParaView. Erase everything from the previous visualization. Navigate to the, let's see, here it is, to one of the 1968 data files. So hit apply. So here's my data set, and I already have the surface view. So I'll switch to color by the ice sea level, by the sea ice levels. So I know that the variable itself goes from 0 to 1, but you can see that in the color bar, the variable goes to 10 to the 20, and that actually, so 10 to the 20 level corresponds to continents. So I will remove the continents by passing the data sets through the threshold filter. So because my data actually goes from 0 to 1, so I can just keep everything, let's say, from 0 to 100, hit apply. So that will remove the continents, and then I will switch to color by, sorry, I'm already coloring by the sea ice level, and then the range goes from 0 to 1 of the variable, so I need to rescale my visualization, and here it is. So here I have a single, the first frame corresponding to January 1850, so now I'm not actually sure where the data is coming from, because obviously nobody had the observatory set up at the North Pole on, well, in the mid-19th century, but apparently the data set is available, so I'm not sure whether it's coming from some other, well, reconstructed records, not sure. So, and you can see that we can observe both the North and the South Pole. So you can see the ice levels around the Antarctic continent through the hole in the North American continent. So what I will do now, so I can use the trace tool to generate a script, and inside the batch.zip file, I already have a script called, let me just load it into the text window, called evolve1.py. So you can certainly study it, but I mean, the idea here is very simple. So we'll load the data set, and then we set up our visualization, and then we and then we save the screenshot to a file. So let me go back to the slides. So to run the script, again, you just use PV batch, and I enclose the main body where we actually do visualization of the script into a loop. So I run the loop index from 0 to 9, so that produces 10 images. And then so I read the corresponding data file, right? And then I output a corresponding, the corresponding image for the data file. So the script is saved as evolve.py in the batch.zip directory. And if I run the script, it will generate 20 objects in the pipeline browser. So one object, for each time step, I have the data set reader, and then the filter, the threshold filter, right? So if you run the script, so if you change the variable, the upper level, the upper limit of the variable from 10 to 1968, and try to run the script in ParaView, ParaView will just crash for you. So what you do, you have to basically delete at the end of each loop. You have to delete currently, the objects they have currently loaded into the visualization pipeline. So you need to delete the threshold filter, and you need to delete the variable containing the data set. So if you do it properly at the end of each loop, then the loop will then the script will run just fine for you. So the modify script is called evolve3.py, and it produces 1968 frames that you can merge into a movie. So I'm going to show you the movie called, so it's called Ice Cover. So open Ice Cover again, because I'm using this, so it will not run very nicely, perhaps on your end, but it will run, well, you will get an idea. So basically it shows all nearly 2,000 frames of this data set, and so that you see seasonal variations when the ice cover decreases in the northern hemisphere, it increases in the southern hemisphere, and vice versa. So the best way I'm just showing this example to stress that it's important, really important, to do proper garbage collection when you put things into a loop inside ParaView's Python. So the better way to run the script, the better way to do this visualization is actually to use ParaView's built-in ability to produce animations of a sequence of data files or a sequence of variables inside the same data file. So I have a script called evolve.py, which actually loads the original netcdf data file containing all 1968 frames, and then it organizes an animation out of these frames. So you can actually do everything inside a single, script without any loops in ParaView's Python. So, and again, we are running out of time, so I won't really show you how to run. You already probably know how to run this script, so, but I just won't show it live in this presentation. So when you run the script remotely on a cluster, you might run into this problem. I just want to mention it. So for example, if you're running interactively inside a scheduled job, so the very first method, remember, where I started the job, I waited for an interactive prompt, and then I set up the display variable, and then I ran pv bash, passing the script name to it. So if you do this, if you use this exact script, evolve pour.py on the parallel cluster, you will get a nice, you'll get a set of images, but if you look at individual images, you will see that they will contain these artifacts. And so these lines, vertical and horizontal lines. And the problem here is that you run the script. So in the script, we set up the resolution. So let me just go display the script, evolve for pi. So you set the resolution of your visualization. So it's 1246 by 882. And that resolution actually exceeds the resolution of the virtual display of X11 on the GPU where you're running your visualization. So there, so the default visualization is set to 1024 by 768. So you have two options basically. Either you can decrease the resolution in your script, or you can let us know that you're running into this problem and we'll try to increase the resolution. And I think it should work without problem. We'll try to set up a high resolution inside the virtual display on the GPU where you're running your simulation. So I'm almost running out of time. So the very last slide in my presentation is about ParaView Cinema. So this is a new feature in ParaView. So it was released first in September last year. And the idea here is, so what it lets you do, you can generate a large number of, so for visualizations that are very expensive to render. So for example, you're doing a time-dependent rendering and each frame takes, I don't know, 5 minutes to render, let's say. So you can't interact with this visualization in real time, right? You have to run it as a batch visualization job, and then at the end you get a bunch of images. Then, for example, you can merge into a movie and then just run this movie. But you can't really interact with this movie, so it's just going to be a movie that you can run and that's it. So the idea of ParaView Cinema is you can set up visualization that generates a large number of images, pre-rendered images from a batch job on a cluster. And then you can load these images into this tool, ParaView Cinema, which is basically a JavaScript. So it's a collection of JavaScript functions, the ParaView Cinema viewer, that you can load into a browser, and it will let you view these pre-rendered images as if you were doing live visualization. And you can do quite complex things there. So you can, for example, zoom in and out. You can pan an object around the screen. You can spin it around. You can turn on and off various views and filters. But of course, all of this is limited to the set of images that you have, that you pre-rendered. So ParaView Cinema currently does not have documentation. So you can download a set of examples from the GitHub address that I have on the screen and play with this. So I managed to make several examples work. Unfortunately, there's still no online, no official documentation. So in my opinion, it's not entirely yet ready for end use, but it certainly looks promising. And I've been really interested in this for the past few months. So I'm going to show you an example of of a visualization, interactive visualization using pre-rendered images using one of the examples. So let me just, so I need to start a web server on my laptop. Let me just do this. So I need to copy and paste these into terminal window. So this will open a web browser. And let's see. Here we go. So this is a pre-rendered visualization using one of the standard VTK examples. And so here I have a bunch of views. So I'll just highlight just one of them, so make the other ones invisible. So here we're looking at three temperature isosurfaces, so 300, 600, and 900 degrees. And so these are live images, so I can actually use my mouse to move it around in 3D as if you were doing live visualization, but of course all of these are pre-rendered images. So I can, for example, delete an isosurface. Let's delete these ones. So I have now only an isosurface at 300 degrees. So I can switch to a different isosurface, let's say 600 degrees. So here we go. And you can sort of interact with this. You can actually zoom in and zoom and so on. So you can switch to a different view. So let's go to a clip filter. So here we go. You see, so you get the idea. So basically, these are pre-rendered images that you organize inside a database. And the way you would do this, you will have to use a ParaView Python script that will construct this specially formatted database that you will load into this JavaScript engine. Then you can use, you can run inside a web browser, and you can do it locally on your machine using the local web server, or you can certainly do it on a remote machine, for example, on a cluster as well, doing visualization, viewing remotely generated images using the web browser. So I think we are running currently, so it's almost 12 o'clock now. I will stop here and pause for questions. So if you have any questions, please let me know. So you can type the questions in the chat window in this video desktop tool, and also you can. I think everybody's muted right now, but we can try to unmute it, or Aaron can try to unmute it, and so you can try to use audio as well. So a question, can we have the link to this presentation as well as the badges you were just used? Yes, certainly. So if you look at the chat window, the links are there. So the link to the presentation is bit.ly pvslides /pv slides. So that's a link to the PDF file. And bit.ly/pv archive is the link to the longer codes that didn't fit into the slides. And Aaron is just pasting those links once again into the chat window. And I will show the first page of the slides where I also have these links. So here they are. Okay. Any other questions? So I'm not getting anybody's audio, so I think it's currently muted for all. So let me just try to unmute it. I think it's unmuted, so yeah. So you can use audio to ask questions if you want. So another question, how smooth is the cinema rendering on your laptop? It looks like you're only getting 1 to 2 frames per second. So it depends. So for the examples that I showed, it's extremely smooth. It's very, very smooth. It's many, I don't know, 10, 20 frames per second. I showed you very simple examples. So especially the first one, it looks really, really nice with many, I don't know, many frames per second. So the reason why you saw only a few 1 or 2 frames per second is because of the video presentation software. So the video link has a limited bandwidth. And unfortunately, when I show live videos inside on a shared desktop, it doesn't show very nice. Can we get access to WestGrid from other? Oh, sorry. So the previous question was how smooth is it the cinema rendering? Oh, okay. Sorry, the cinema rendering. So it was not smooth on my desktop. Sorry, I didn't understand the question. It was not smooth on my desktop simply because it was limited to the number of images that you pre-generated in this example. So this example just contained, I don't know, 10 or 20 images in total for each filter. So that's why it was not smooth. But if you generate a larger number of images, then it's going to be much smoother. So can we get access to WestGrid from other Canada nodes, Compute Canada sites? Oh, for sure, yes. So anybody in Compute Canada can get an account on any cluster in Compute Canada. So historically, we had several consortia. Well, we still have them: WestGrid, SharkNet, SciNet, and so on. And historically, we've been serving only the local institutions. But in the past few years, we actually opened up, so anybody in any Canadian university can easily get an account on any cluster in Compute Canada. So if you're, let's say, from Toronto or from Halifax, you certainly can apply for an account in WestGrid, and it's very easy to do. Just go to the online documentation. And vice versa, anybody from Western Canada can get an account, let's say, on an Orca cluster in SharkNet or somewhere in AceNet and so on. Okay. Any other questions? Okay, if not, if there are no other questions, then thank you very much, everybody, for attending. So I hope it was useful. There is a link to the evaluation form in the chat window. So if you have a few minutes, please feel free to fill in that questionnaire. And you can certainly ask me questions simply by emailing me at any time. I'll be very happy to help you with your specific visualization. So thanks, everyone, and that's it.